All right. Hello, everyone. My name is Evangelos Zimbeloudis, and the topic of my presentation is on CTS, or continuous toe shearing, which is a novel manufacturing process which expands the overall design space for composites. Now, as you all know, composites are only strong in the fiber direction, and we compensate for this in order to give sufficient strength in all the critical directions by stacking layers of straight fibers together. But if you look at nature, we hardly see any straight fibers. What you see here is articular cartilage, a high-tech composite found within our bodies, where, as you can see, not only the density, but also the orientation of the collagen fibers constantly changes in order to adapt to the complex loading condition. Could we then design structures like this, structures which mimic nature and would allow us to improve the efficiency of our components? Well, the first step in doing that would be the ability to control the path of the fibers, something known as fiber steering. Now, fiber steer designs could yield significant performance benefits. For example, what you see here is a fiber steered wing skin, where the optimally steered paths could distribute the load directly onto the wing stiffeners and thus achieve a weight reduction of approximately 10%. Furthermore, as fiber steering allows us to tailor the stiffness of a structure at any given point, it makes it possible to aeroelastic tailor aircraft structures. More importantly, however, since this is a new field in structural engineering, we haven't yet fully explored the expanded design space that it opens. Now, this is all great, apart from the fact that modern placement machines cannot produce such optimized designs. And to understand this, we would have to look at the current state of the art in composites manufacturing, the automated placement machines, which basically place bundles of fibers on the surface of a mold using a material deposition head. Now, although these machines are excellent at laying straight lines, they have very limited steering capabilities. And the reason is that they try to bend the tapes in order to steer the path, and this creates buckling, and buckling leads to all sorts of defects. Now, to overcome these manufacturing complications, the concept of continuous toe shearing was developed here at the University of Bristol by Eric Kim. Now, CTS exploits the material's shear deformation in order to steer the fiber path and results in no buckling and no defects whatsoever. So since conventional machines rely on bending, there is a strong coupling between the material width and the minimum steering radius. This is the radius that can be achieved without the introduction of significant defects. Basically, what this means that for AFP and ATL, the narrower the tape, the better the steering capabilities. On the other hand, since CTS relies on shear deformation, there is no coupling between the material width and the steering radius, and we can exploit this by laying up much wider tapes in order to boost the productivity of the process. So let's take an example. 100 millimeters is a standard tape width for ATL, and this would result in a minimum steering radius of 11,000 millimeters. CTS, on the other hand, can do 50 millimeters. This is several orders of magnitude lower, and essentially CTS is the first process that allows for wide tape layup with steering capabilities. Give it a sec. So this is a video showing a layup with CTS using dry fabric. Now, when we use dry fabric, we have two options. Either we can attach the tape on the surface of a mold using binder, or we can attach a resin tape within the head to impregnate the preform. Now, as you can see with the second option, the head layout is much more complicated, but it reduces the manufacturing steps. Now, while shearing dry fabric, the quality is primarily affected by material parameters, such as the weft yarn pattern. And although with these materials we cannot achieve the best quality possible, it is an overall low-cost and very robust process with highly flexible material selection. Now, very recently, we were able to expand CTS for use with prepreg. And what was key here was the ability to control the tension of the fibers while shearing. Now, with prepreg, we can achieve much higher quality. And due to the high mechanical properties of the material, we can produce components of high structural integrity as well. So what we have seen is that nature designs in a completely different way to man. And to mimic nature and improve the efficiency of our structures, we would have to escape the straight fiber paradigm. The first step in doing that would be to enable fiber steering capabilities in modern placement machines. And to do that, we have developed the concept of CTS, which operates in a niche application field, as it allows for wide tape layup with steering capabilities, something which was not possible before. More importantly, however, since this technology expands the overall design space, this technology could shape the next generation of ultra-efficient aircraft. Thank you very much for your attention.